Good morning, everyone. Today I will introduce Experiment 4, Microcomputer-assisted automatic potentiometric titration. This experiment demonstrates how modern analytical instruments and computer control can improve the accuracy and efficiency of titration experiments. First, let us look at the purpose of this experiment. Traditional titration methods have several disadvantages. Normally, titration is performed manually using a burette, and the operator must carefully add the titrant while recording the volume and pH or potential values. This process is usually time-consuming and complicated, and it may also be difficult to determine the exact endpoint of the titration. To overcome these problems, an automated titration system is used in this experiment. Now, let us discuss the principle of the automatic potentiometric titration system. In this system, a microcomputer controls the titration process. The computer sends a digital signal, which is converted into an analog signal using a digital-to-analog converter, or DAC. This signal controls the syringe pump, which adds the titrant at a programmed flow rate. The pH electrode measures the potential of the solution, and the small signal is first amplified by an operational amplifier. Then, the analog-to-digital converter converts the signal into digital form and sends it to the microcomputer. Finally, the computer processes the data and displays the titration curve and results on the screen. These following materials are required to prepare the solutions and perform the automated titration. For this experiment, we use an IUT 501 automatic titration, which includes a syringe pump, pH, electrode, and microcomputer system. Other instruments include a magnetic stirrer, beakers, and volumetric flasks. The chemicals used in the experiment include hydrochloric acid solution, sodium carbonate solution, and buffer solutions for pH calibration. Now let us look at the experimental procedure. Step 1. Preparation of 0.1 meters HCl. In the first step, we prepare a 0.1 molar hydrochloric acid solution by diluting concentrated HCl with deionized water. Step 2. Calibration of HCl. Next, the prepared HCl solution is standardized to determine its exact concentration. This calibration process is usually repeated 3 times to obtain accurate results. Step 3. Titration of unknown sample. After calibration, the standardized HCl solution is used to titrate an unknown sample, which contains sodium carbonate. The automatic titration system records the pH changes and generates a titration curve, which helps determine the equivalence points. Repeat experiment 3 times to improve accuracy and reliability, and the average value is used to minimize experimental errors. Before starting the titration, several steps must be performed to set up the instrument. First, clean the pH electrode with ethanol and deionized water. For electrode calibration, press F5, then 2, then 1 and set electrode channel 1. Then pH electrode must be immersed in standard buffer solutions, usually pH 6.86 and pH 9.18, and press start to ensure accurate measurements. Next, the titration method is set in the instrument. Set titration method, press F1, then 1, then 3, then enter. Again, press F1, and then press 2. Parameters such as the titration method, differential, thresholds for equivalence, and maximum titration volume are entered into the system. After that, the titrant storage bottle is cleaned and filled with the titrant solution. Then, the pump and pipeline are washed with the titrant to remove any remaining solution and avoid contamination. First, the storage bottle must be cleaned properly to remove any remaining chemicals from previous experiments. This is important because contamination can affect the concentration of the weighed titrant and lead to incorrect results. After cleaning, the fresh titrant solution is added to the storage bottle. Remove the titration solution nozzle from the fixed frame and Place in the titration for mean. Clean the titrant nozzle in waste beaker. Then press purge, then 3, and then press enter. Press. Ready to return to the standby screen. Once the system is ready, the titration can begin. First, the pH electrode is cleaned and placed into the sample. Solution. The solution is placed on a magnetic stirrer to ensure proper mixing. After the pH reading becomes stable, the start button is pressed and the automatic titration begins. The instrument automatically adds titrant, measures the pH changes, and records the data. Repeat experiment 3 times for accurate readings. After the experiment is finished, the system must be properly shut down. The pH electrode is cleaned, dried, and stored in saturated potassium chloride solution to maintain its stability. The titrant nozzle is also cleaned and placed back on its holder. And finally, the power supply of the instrument is turned off. After the titration is completed, the data obtained from the LESH instrument are used for calculations. First, we calculate the true concentration of the HCl solution. Then we determine the percentage of sodium carbonate in the unknown sample. In addition, the titration curve of sodium carbonate can be used to estimate the Pa and pKa values of carbonic acid, and these values can be compared with the standard literature values. First, always wear safety gloves and goggles when diluting concentrated HCl to protect yourself from chemical splashes. Second, make sure to calibrate the pH electrode before starting the titration. This ensures that the pH readings are accurate. Third, always rinse the pH electrode with distilled water before and after each measurement. Fourth, do not move the beaker while the magnetic stirrer is rotating to avoid damaging the pH electrode. Fifth, wash the syringe pump and pipeline with titrant before titration. Finally, store the pH electrode in saturated KCl solution after the experiment to maintain stability. Finally, discussion questions focus on comparing the automatic, potentiometric titration method with traditional acid-base titration methods, and also understanding the role of important electronic components such as digital to analog converters and analog to digital converters in the automated system.